Good morning, everybody. It's time to get started. Hopefully, you've had a chance to do this first problem for exam review. We are going to do a few more questions after this as part of our exam review, and then we're going to start with Chapter 7. So I'm going to go to a new slide here to go over this, one that has the periodic table, and we'll get started. Did anyone have any specific questions, or do you just want me to go over it? If you have specific questions, you can let me know. Otherwise, I'll just go over how to write these configurations. We'll start with iron. Now we're supposed to be doing the noble gas configuration. Iron is in the fourth period, which means that we want to use the period 3 noble gas. And all of our noble gases are in this group. The one that we're looking for is argon. Then we add everything that's in the fourth row. So that's the 4s here, and this is the 3d. And we count 1, 2, 3, 4, 5, 6. So that's for iron, and that's a neutral atom. Now we need to do phosphorus. Phosphorus is in group 5A, so when it forms an ion, it is a 3- ion. That means it's going to gain 3 electrons. 1, 2, 3. So it too will look like argon because it will have 18 electrons. And the last one is strontium. It's got 38 electrons. It's a metal, so it's going to lose electrons to become an ion. That's why it's a positive ion. And it loses 2 electrons because it is in group 2A. When it loses those 2 electrons, it's going to end up with 36 electrons, like krypton. Questions here? Let me know if you're ready to move on. Okay. Let's keep going. So this question is one that's on the exam review, but I like to go over it just as a refresher. So I'll give you about a minute or so to read through the problem and start it, and then I'll hop back on and we'll talk about it. Okay. So this one, calculate the predicted atomic radius for selenium given the atomic radius of sulfur and tellurium. This is a problem that goes kind of back to chapter 5, where you can predict physical properties. So So I wanted to remind you guys of these types of problems. What you need to know here is that sulfur, selenium, and tellurium are all in the same group. And selenium is between these two elements. So when you're looking at this question and you know the radius of sulfur and tellurium, selenium should have a radius that is somewhere in between 104 and 143 picometers. So without doing any kind of math, the only one that fits the bill, yeah, 124. So you don't even have to do any math. That's the only answer that makes sense. It has to come between the radii of selenium and tellurium. Questions here? Or are we ready to move on? Because you'll definitely see ones like this. Atomic radius or density. You'll have to do some predicting. This is a chapter 6 question. Well, I can show you how to do the math for this one. So here we've got something that's in the middle, right? So the difference between tellurium and selenium, you take 143 minus 104, and that gives you 39 picometers. Then what you do is you divide that in half, because selenium is going to be kind of in between these two. 39 is almost 40, so you can just call that selenium should be approximately 20 picometers larger than sulfur. So 104 plus 20 gives you 124. Does that help, Khadijah? You're very welcome. So here's a chapter 6 problem. Don't forget to classify and write the chemical formula. So you got to do both of these. I'll give you a couple of minutes to get started, and then I'll jump in and start writing I'll first write your choices, just in case you forgot. So there's binary ionic compounds, ternary ionic, binary molecular compounds, binary acids, and ternary oxyacids. So those are all the choices for classifying. Classify, write the chemical formula for these 3 compounds. I'll check in about 2 minutes. Alright, I'm going to start classifying here. You can jump on in if you want to. We're going to classify A, B, and C. Then I'll write out the chemical formulas. So A, we've got zinc carbonate. How do we classify that one? You can use the abbreviations up there. Yep, this one is a ternary ionic compound. Metal, plus one of those polyatomic anions. What about B? We've got tin 4 chloride. Binary ionic. Metal plus a nonmetal. And C? Clean sweep, Malachi. Binary molecular. The giveaway here is that you've got two nonmetals, so nitrogen and the ox, but also these prefixes are giveaways that it's a binary molecular compound. All right, chemical formula. Zinc carbonate. That means we've got a zinc ion and we've got carbonate. Those, if I had one of each, then my total charge would be 0. So I can just slap it together like this. That's zinc carbonate. Tin 4 chloride. Tin 4 tells me that it is 4+. Chloride tells me I'm looking at chlorine. You take the group number, subtract 8, and that gives you -1 because chlorine is in group 7A. I've only got, if I took one of these tin ions and one chloride ion, that's not 0. So I've got to do my swapping trick. And I end up with SnCl4. Dinitrogen pentoxide, probably the easiest one to do. Tells you that you've got nitrogen first. Di means 2. Pentoxide, the ox comes from oxygen. So that's our second element. Pent comes from that prefix box, and that means 5. Questions here? So the carbonate ion is CO3 2-. When you look it up, that's what it is. So I just took one zinc ion and one carbonate ion and put them together. And you will get that polyatomic ion sheet with your exam, so you don't have to memorize them. Other questions, or are we good to move on? Yeah, so when we do parentheses around the polyatomic ion, that means that we need to have more than one. Here, we didn't need more than one carbonate ion, so we don't need to do parentheses. You're welcome. Alrighty. So that's our review. Exam is only on chapters 5 and 6. I pulled some of the questions that typically students have issues with, but y'all seem to be pretty good. Make sure you go through that exam 3 review packet. It'll really help you. Just to go over the details for the exam, this is our third one, so y'all are pretty much experts at this point. Tomorrow, an exam 3 folder will suddenly appear. It's going to have the polyatomic anion sheet and a periodic table. You can print those out. There will also be a link for exam 3. Make sure that when you're ready to take the exam, that you open Respondus Lockdown browser and then navigate to Blackboard. The exam will be similar in length as the last one. Multiple choice, matching, fill in the blank, that kind of thing. So there's really no work to show. So we won't be showing work for this one either. Any questions about how to access the exam or anything like that, it is available, or it will be available, Wednesday, which is tomorrow, March 17th, through Friday, March 19th. And that's till 11:59 p.m. Eastern Time. The exam will be available tomorrow by 9 a.m. I have office hours today. If you need to set up a meeting with me, you can set up a meeting for tomorrow morning. How many do you have left? You have one more exam after this and then the final. So exam 3 is on chapters 5 and 6. Exam 4 will be on chapters 7 and 8. And then the final exam will be like an exam on chapters 9 and 10, plus, it'll be like 1.5 exams. So you'll have a chapter, 9 and 10, and then some review from all the other chapters. Look, I was looking at the syllabus like, wait a minute, we're there already? Yes, thank you for bringing that up. So the extra credit that I offer for everyone, so there's always extra problems on the exam. So you can score more than 100% on the exam, or you can, miss a few problems and still get 100%. In addition to that, on Mastering Chemistry, there's what's called the Chemistry Primer. That is extra credit. What the Chemistry Primer is it's a collection of problems from all the chapters that we have already covered and the ones we will cover. So you can use it as review if you want to save it and do it, before finals. But this is a way for you to make up some of the points that you may have lost in Mastering Chemistry, since it's such a big chunk of your grade. So you can work on the Chemistry Primer at your own pace, and it's available up until the middle of finals week. Our final on finals week is that Tuesday, which I believe is May 4th. And it's at 8 a.m., so it's pretty much class time. You will have until, I believe, Wednesday, May 5th, to complete that Chemistry Primer. . other questions about the semester, where it's going, anything like that? All right. Well, come on to office hours if you need some help or you just want to say hello. We're going to start chapter 7, and that's chemical reactions. Um, this you need to remember your chapter 6 information for. So if you don't remember naming, if that was a struggle for you, then chapter 7 will be a little bit difficult. You're also, we're building from here on out. Chapter 8, you're going to need to remember balancing equations, and we're going to start reaching back towards some of that conversion math like we did in chapter 2. So we're coming full circle here. Just to give you a heads up, if conversions weren't your thing, you might want to review that before next week. So that's also something that you can come to office hours for. Once we finish chapter 7, the remaining chapters we're going to slow down a little bit and take 2 class periods per chapter for the rest of the semester. So we'll do chapter 7 all today, and then chapters 8, 9, and 10 we're going to take 2 weeks on because they're all math. So we'll get in all the concepts, and then we'll get in a lot of practice as well. That seems to help everyone do well. So as long as you come to class, you watch the videos, do the homework, you'll be good to go. Okay, we're going to start with the evidence for chemical reactions, which we talked about a little bit in chapter 3 when we were talking about chemical changes and chemical properties and things like that. But I'll review them quickly here, and then we can do some practice. So the 4 observations that indicate a chemical reaction is taking place. You don't have to see all 4, you just need one. First one, a gas is produced. If you've ever seen somebody take an Alka-Seltzer, maybe someone that's older, you put that big white pill into the water and you see all the bubbles, that's a chemical reaction. That fizzing is the release of gas. And that's one way to see that you've got a chemical reaction taking place. The second way is that an insoluble solid is produced in a solution. So you've got 2 aqueous solutions, which just means 2 things dissolved in water. You mix them together, all of a sudden you have a solid form. That solid is called a precipitate. It may be colored, like in this image. It could be white, which a lot of substances are white. But either way, if you see a solid form when there was no solid before, that's a chemical reaction. The third way is a permanent color change. So oftentimes it has to do with metals and replacement reactions, which we're going to talk about. If you see a color change and it stays that way, then you formed something new. The final way is energy change. So that means a reaction is going to release heat or absorb heat. You'll need to know the terms exothermic and endothermic. So exothermic is a reaction that releases heat. Endothermic absorbs heat. With an exothermic reaction, your flask gets hot. Endothermic, your flask gets cold. So those are the 4 pieces of evidence that you can use to say, hey, that's a chemical reaction. So we went through that a little bit quick, but it's something that's pretty easy to catch on to. So let's do a little bit of practice. It's like my game show, chemical reaction or not. So in the chat, you can write CR for chemical reaction, or you can say no, nah, whatever. Number 1, toasting bread in a toaster. Chemical reaction or not? It is a chemical reaction. So when that bread gets brown, you're actually doing chemistry. The heat is changing the proteins and the carbohydrates on the surface of the bread. And doing so makes it turn brown, makes it smell great, and taste better. Okay, so that is a chemical reaction. Dry ice sublimes. Number 2. Is that a chemical reaction or no? Yeah, so this is not a chemical reaction. It's a physical change. Okay. Third one. 2 clear liquids are combined to give a purple liquid. Oh, sublime. So it's okay to put your answers in the chat. So that means that's a harken back to chapter 3. Sublimation means that you're going directly from a solid to a gas. And that's what dry ice does. Dry ice is solid carbon dioxide. It's super duper cold. You leave it on your lab bench, it just starts to smoke. That's carbon dioxide. It just goes straight from the solid to the gas. Okay. So the third one, I see folks put in chemical reaction, and I agree. You've got a permanent color change, a purple liquid. So that's the kind of thing that you'll need to do for chapter 7. It's pretty much a review of chapter 3 in that regard. Yes, it does. But it's still carbon dioxide. There's no chemistry going on. It's just a change of state from a solid to a gas. Yeah, a little bit tricky. A little bit tricky. But this is from chapter 3. So if you need some more review on that, you can hit that chapter back, do a little bit of review from there, and you'll be good to go. Next, we're going into chemical equations. Yeah, you're welcome. We're going to take a chemical equation and write it in words, and then we're going to take a written description and write it as a chemical equation. So that's what we're heading to right now. This chart, I highly recommend having it in your notebook or just having this, page if you screenshot it or something like that. If you've never written chemical equations before, it'll be helpful to have all these symbols at the ready. So with an equation, you're always going to have your reactants on the left-hand side. Then the arrow, which is the yields or produces sign, and then your products. If you have multiple reactants or multiple products, you're going to put a plus sign between them. Sometimes over this arrow, you'll see a delta, a little triangle. That's for heat, so it's like the tip of a Bunsen burner. Or you might see iron or palladium or some other element. That's a catalyst. So it's saying that you have an iron catalyst or a platinum catalyst. It's not consumed during the reaction, it's just present. If you mix two things and there is no reaction, then you write NR. And that will come into play more when we talk about the different types of chemical reactions. And whenever you're writing a chemical equation, you need to include the states of matter that each compound is in. So we can do some practice of this. I'll show you how we go from the chemical equation to the written description. So am I good to move on to the next slide? One more thing. I always forget about this. You will see that some elements are written as two atom molecules. And you'll need to know what they are when you're writing out your chemical equations. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Hydrogen is already kind of strange, so it's just going to do its own thing. The others form a 7 in the periodic table. All of these are called diatomic molecules. They like to hang out in pairs. So when you're writing your chemical equations, make sure that you write these properly. You'll need to remember these. Now we can do a chemical equation. Starting with the simple one. I'm kind of going to walk through it with you, and then I'll let you do some practice. What I like to do when I'm writing a chemical equation in words is I go through and name everything first. So I write out what I have. So when you see something on its own, a metal on its own like this, you can just say cobalt metal, sodium metal, whatever metal it is. O2, that's our oxygen. And that G in parentheses means that it's a gas. Now we've got a compound to name. I see I have a metal plus a nonmetal. So it's going to be a binary ionic compound. Cobalt is a transition metal, which means that it can have more than one ion, right? It can form more than one ion. So I need to figure out what ion cobalt is. I do that by looking at the anion. I've got 3 oxygens, and oxygen I know is 2 minus. If I've got 3 of them, then that means a -6. I've got 2 cobalts, so that means that I have to have a +3 for my cobalt charge. And the name is cobalt oxide, cobalt 3 oxide, and it's a solid. So all of that is chapter 6. Now we put together the words. You always start with your reactants, then the yield sign, then the products. My reactants, I've got cobalt metal, which when you say cobalt metal, you know that it's a solid. You could also say solid cobalt here. And oxygen gas. Now we get to the yields part, and we see the triangle. So that means heat is added. We can say are combined with heat. To produce. And then we say our product. Solid cobalt 3 oxide. So let's show you where we got everything from. All of our reactants, right there. Then we did the yield sign. Then we did our products. Does everybody see how I put that together? Reactants, the yield, then the products. It's always the same. Now in terms of, the exact language, this yield sign, you can say produce, give, yield. They're all the same thing. So you have a little bit of creative leeway there. But if you just want to be able to plug it in and say the same thing for all of them, you can say are combined to produce. And that will work pretty much with everything. There's only one reaction type where that doesn't work. And I'll cover that when we get there. But I want you to try one on your own. A little bit more complicated. Might take you a little bit longer to name everything. But I'll give you about 3 minutes to work on this. Name everything and write it out in words. I'll check back in 3 minutes. Okay. I will start naming things and write out what I would say to describe this chemical equation. It may not be the exact way that I write it. If you wrote it a slightly different way, that's fine. What matters is that you have all of the names correct and all of your states of matter. And if there's like a yield, like a with heat or a catalyst of some kind, that's listed too. Alrighty. Unless someone needs me to, I'm not going to go into detail about how I'm naming these. Oh wow, you put it in the chat. Look, I wouldn't even have asked you to. And I'm gonna be honest. If I was a student and someone said, "Oh yeah, put your answer in the chat," I would have been like, "Somebody else can." So thank you for that. Ah, okay. So what I wrote: aqueous solutions of lead 2 nitrate and lithium chloride are combined to yield solid lead 2 chloride and aqueous lithium nitrate. So something like that, you're good. Questions here? Then let's do a practice where we write the chemical equation from the written description. So I want you to try this. Read through and write it out. Don't forget to include the states of matter. So try writing the chemical equation from this written description, and then I'll hop on. I'll give you about a minute, minute and a half, and then I'll write it out. All right, I'll start writing this one out. No need to write it in the chat. You can just check your work. We've got aqueous solutions of lithium iodide and silver nitrate are mixed to give silver iodide precipitate and aqueous lithium nitrate. So what's highlighted in yellow describes our reactants. The orange are mixed to give. That's the yield sign. And I'll highlight in green the products. So this same kind of word formula is what you're going to see in all of the written descriptions of chemical equations. Now we write it out. We've got aqueous solutions of lithium iodide and silver nitrate. That's that. Our mix to give, I'm going to draw my yield sign. Silver iodide precipitate. That just means that it's solid. And aqueous lithium nitrate. Questions here? Okay, it's pretty straightforward. So what I will say is that for your homework and especially for the exam, just pay attention to detail. Don't forget your states of matter. If something is, combined with heat, don't forget about the little delta sign, those kinds of things. On the exam, these types of questions will be multiple choice or fill in the blank. And you'll have to either choose the one that describes the chemical reaction or choose the chemical equation that matches the written description. So there, you'll have to make sure that all the pieces are right. So if I gave you this and I left out, all of the states of matter, you wouldn't want to choose that one. So it's just, these questions are more like a reading and comprehension exam than it is testing what you know, because you know how to do it. It's not hard. But you may overlook something if you're rushing. So don't rush. Take your time. Now we're going to move to classifying chemical reactions. These are the 5 reactions that we're going to talk about. I'm going to go over them pretty briefly. We'll spend a little bit more time on the replacement reactions. And then after we go through all of them, I'm going to write out kind of a cheat sheet for you. So I would recommend having that cheat sheet in your notebook. It'll help you study. It'll help you with your homework. So we're going to get started. We're going to go over all of these in this order, starting with combination reactions. So a combination reaction, you're taking a few simple reactants, combining them into something that's more complex. That is a combination reaction. You might also see it called a synthesis reaction. They're the same thing. There's some examples of combination reactions, taking a metal and oxygen gas, making a metal oxide, non-metal and oxygen gas, non-metal oxide, metal and a non-metal, you make an ionic compound. So those are just some examples that you might see when you're doing your homework, or if you want to do some extra practice, which I always post extra practice for chapter 7. But this is the key right here. Multiple simple reactants, one complex product. I'll kind of linger for a few extra seconds in case you're writing something, and then I'll move on. And if I move on before you're done, just let me know and I'll go back. Second reaction type, decomposition reactions. We've got a single complex compound that's broken down into multiple simpler substances. Oftentimes, you're going to need heat to get the thing going. Not a requirement, but oftentimes you will see heat with a decomposition reaction. If you're writing out the written description of a decomposition reaction, you've only got one reactant. So you're not going to say that one compound is mixed to combine. So here, if I were writing out this equation as a written description, I would say mercury 2 oxide decomposes to yield liquid mercury and oxygen gas. So that's the only one where are combined to yield. That doesn't really work because you can't combine just one thing. That's decomposition reactions. Okay. Let me know when you're ready. Next, we have single replacement reactions. Here, what we're looking at is a more active metal displaces another less active metal in a compound. So let's say that I've got some iron, and I want to add that to a solution of copper 2 sulfate. When I add that iron, it is more active than copper. So what it's going to do is kick the copper out of solution. Say, look, get out of here. I will now take up residence in this solution. And the iron will replace the copper in the aqueous solution. So what you can actually see when this happens is you'll see the copper kind of plating onto that iron source. So this picture is like an iron nail, and then you stick it into the copper 2 sulfate, and you'll start to see the copper. So this is copper. Now you might be asking yourself, how do I know what metal is more active than another metal? Good question. There's the activity series. The activity series just gives you the relative order of the most reactive to the least reactive metals. I'll go back. Yeah, you can just say wait, and I'll hold up. So you need to know the activity series. You don't need to memorize this. You just need to know how to use it. Lithium is the most active metal. Gold is the least active. Everything else in between is here, relative highest to lowest. You'll also notice that there's hydrogen here. Hydrogen isn't really a metal, but under the single replacement umbrella, we can have aqueous acid displacements, and I talked about that in the YouTube video, the pre-recorded one. So if you have an acid and a metal, if the metal is more active than hydrogen, it can replace it. Same thing with water. So there are some elements, some metals, that are so super active that they will replace the hydrogen in water. You don't have to know those specifically. Those are just two kind of subtypes of the single replacement reaction. So watch that, make sure you understand that, and you can recognize it as a single replacement. Right now, I want to do a little practice with the activity series to make sure that you know how to use it. I've got 3 little problems for you to do. And in each one, I want you to choose the more active metal in each pair. The first pair we have is iron and copper. We just talked about this one, but I will do this one just to show you, and then you can do the other 2. So I'll show this one in red. Here's iron, here's copper. The one that comes first is the most active. So iron is more active than copper. I'll give you a second. We've got strontium and potassium. Which one is more active? You can put your answer in the chat. Yeah, the potassium is more active. We've got potassium here, strontium here. Third one, we've got lead and nickel. Which one is more active? Here's nickel, here's lead. So that's how you use this activity series. Let's do some single replacement practice questions. I've got your relative activity series down below. We'll talk through the first one together, and then I'll let you do the second one on your own. Will cadmium replace iron in the following reaction? We've got solid cadmium being added to iron 2 nitrate. What you do is you find cadmium, you find iron. The one that's solid has to be more active than the metal that is in solution in order for it to be replaced. Cadmium, is it more active or less active than iron? It's less active. So will cadmium replace iron in solution? No, it will not. So here we write no reaction. So on that chart with all of the symbols, that's where the NR comes into play. There's not going to be any reaction. Now I want you to try the second one. Will zinc replace lead in the following reaction? And you've got that reaction below. I'll give you a minute. maybe more like 30 seconds. You can put your answer in the chat. For right now, just put, yes or no, and then we'll talk about how to finish out writing the equation. So we got to find zinc and lead. Here's zinc, here's lead. So yes, zinc will absolutely replace lead, happily. But what do we get as our products? The zinc is going to end up in solution with the nitrate ion. And the lead is going to become a precipitate. So hopefully the colors help you kind of track where things go. But you'll need to be able to complete this kind of a reaction. If you have a single replacement, then you're going to swap out. The more active metal is going to be in solution, and the least active metal will be as a solid or a precipitate on its own. So does that make sense? I'm not going to spend time doing a whole lot of practice with these. I have a chapter 7 practice problems, like additional practice, already set up that I'm going to post right after class. So you can get a lot of practice with doing these types of problems. The next reaction type that we have is a double replacement. So with a double replacement, you've got two aqueous solutions that have ionic compounds. You mix them together, and all of a sudden, you have a precipitate. In this example, we have barium and potassium as our positive ions. And they're going to switch anion partners. The barium was with the chloride, now it's with the chromate. And when that happens, it falls out of solution because barium chromate is insoluble. Now you might be wondering, okay, so how am I supposed to know that? There are solubility rules. This table has all the solubility rules you need to know, but you don't need to memorize it. You will, however, need to know how to use this table. The first half, 1 through 5, describes things that are soluble. So if you have alkali metal ions, which is group 1A, or the ammonium ion, anything with that is going to be soluble. Acetate ion, nitrate, the halides, those things are soluble. Sulfates, soluble. But there are some exceptions. I use my angry red for exceptions, okay? Those things are not soluble. Then we have 6 through 10. And this describes things that are insoluble. But we have exceptions here too. And pretty much the exceptions read like this. If it's a group 1A, then it's probably going to be soluble. If it's ammonium, it's probably going to be soluble. There are a few other exceptions too, but by and large, Rule 1 and then a few other exceptions. So these green ones mean that these exceptions are actually soluble. Now that's all fine and good, but what's more helpful is to practice using this. So that's what we're going to do. I'll walk you through how to use the table and decide whether a compound is going to be soluble or insoluble. The first one we have is tin 2 chromate. Chromate is what I'm interested in because that's an ion that I can look up on my table. The rule for chromate ion is that it's generally insoluble in water, except for lithium, sodium, potassium, and ammonium. I've got tin. That's not an exception. So my prediction is that tin 2 chromate will be insoluble in water. Number 2, we've got lead 2 acetate. Take a second, look at the rules, and let me know in the chat whether you think it's soluble or insoluble. You put an S or an I. If you're a little bit stuck, start by looking at the rules to see where you find the acetate ion and see whether or not compounds with acetate are generally soluble or generally insoluble. Rule 2, we've got the acetate ion, and it is generally soluble. There's no exceptions, so it's soluble. Does that kind of logic make sense? Okay, so the first one about the insoluble. So let's just run back the chromate one real quick. We find chromate on our list. It is generally insoluble. The exceptions would be Rule 1, which are soluble. We look at what we have. We've got tin. We check Rule 1. We don't have any of those ions. We have tin 2+. That means that tin 2 chromate is going to be insoluble. If it were lithium chromate or sodium chromate, it would be soluble, but it's not. Everything outside of that is going to be insoluble. Let's do some more practice. what we have here is a potential double replacement reaction. I say potential because we don't know if we're going to form a precipitate or not. If we do form a precipitate, it will be a double replacement reaction. If we don't, then it's going to be no reaction. I'm going to walk you through this one, and then I'll let you do one on your own. We've got two aqueous solutions. We mix them together. I'm going to give my positive ions some color so that we can track them. Instead of having calcium sulfide, we're now going to swap the anions. So I'll have calcium nitrate instead. And the zinc will now be with the sulfur. That's the easy part. You swap ions. Now we need to ask two questions. Soluble or insoluble for the calcium nitrate? I look at my chart. Nitrate ion, generally soluble. Cool. Aqueous. Sulfides, generally insoluble. I've got some exceptions, so let me see if mine falls under that. Calcium, strontium, barium, and then lithium, sodium, potassium, ammonium. Those would all be soluble. I don't have any of those. I have zinc. So that means that zinc sulfide is going to be insoluble. It's a solid. So this is a double replacement reaction. I swapped the ions, and then I asked the question, the two compounds that I form, are they soluble or insoluble? And I circled the wrong one, I just realized that. Insoluble. Much better. If one of your compounds is insoluble, then you have a reaction. If both of them are aqueous, then you have no reaction. So talk to me. How does that feel? You ready to try one? Do we need to talk it through again? It takes practice. But if you kind of understand the method, then I think you're ready to try one. Let's try one. So I'm going to make you do a little bit more work because I didn't write out the chemical formulas. So you will need to do that, trying to help you be ready for the exam. And then do what I did. Swap your ions and then ask each compound, are you soluble or insoluble? I'll give you 3 minutes to do that, and then I'll check in. All right, I'm going to start on this one. We've got lead 2 acetate and sodium sulfate. Those are the reactants. Give my metals some color, and it'll be easier to keep track of them. The lead is with the acetate ion. I'm going to swap it out and put it with the sulfate. So sodium, the sodium ion is 1 plus. Sulfur or sulfate is 2 minus. So I need to have 2 sodiums to balance the charge. So if I were to swap ions, that's what I would have. Now I have to ask each compound, are you soluble or insoluble? Sulfates are generally soluble, but there are some exceptions. And lead 2 sulfate is an exception. It is insoluble. The other compound we have is sodium acetate. This hits actually 2 of the rules because we've got a sodium ion, which if it's got sodium, chances are it's going to be soluble. And the same with the acetate. So our lead 2 sulfate is going to be a solid that's insoluble. And okay, there we go. And then aqueous for the sodium acetate. I just keep running myself out of room. So how do we feel about this one? If we're feeling better, then that's a good sign. So there will be more practice for you to do. Just keep practicing with these solubility rules. And you don't have to memorize them. Just practice using the table because you'll get this exact same table for your last exam and for the final. Last reaction type. We've got neutralization reactions. This is just when you're mixing an acid and a base. Remember that an acid has that hydrogen in front. It's either a hydrogen plus a nonmetal or hydrogen plus a polyatomic anion. So recognize when you have an acid. This is a ternary oxyacid. A base is something that's going to have a metal plus the hydroxide ion, which is OH. You may also see ammonia. That's also a base. And what you produce is a salt, so an ionic compound. That's all salts are. It's an ionic compound and water. Now this may look really similar to a double replacement reaction, but it's not. And the hallmark here is that you make water. So if nothing else, in order to tell the difference between the double replacement reactions and the neutralization reactions, you have to make water. If you don't see water, it's not a neutralization reaction. Let me know if we're ready to move on from this slide. Okay, so before we start filling out our cheat sheet, I'm going to take a quick poll. We don't have a whole lot more left. We're going to do our cheat sheet and balancing chemical equations, and then we're done. Do you want like a short 5-minute break now, or do you just want to finish even earlier? So finish early, or take a 5-minute break. I figured, but I always ask. All right. This is probably one of the last times that we're going to finish early. The other chapters, we're doing math and we're doing a lot of practice problems. Those usually take a while because there's usually questions. So let's enjoy it. 8 a.m. is a strong morning. If I can get you out of here a little bit earlier so you can have some breakfast, then that makes me a happy camper because I get to go and hold my children. I like doing that. They're pretty sweet. All right, let's make this cheat sheet. I've got all 5 of our reactions here. And what I'm going to do is write out either what it is or how you can remember it. Oh, yeah. That is exactly how I feel with my babies. This cheat sheet will help you recognize your reactions. Combination reactions. We said that we've got multiple simple reactants we make one complex product. Decomposition reaction is the reverse of a combination. So if you can remember the combination, you're combining things. Decomposition, you're taking that complex thing and breaking it down. Single replacement reactions. More active metal replaces less active metal in solution. You're going to need to use your activity series here. Double replacement reactions must form a precipitate when you swap those ions. You need to use the solubility rules. That will help you determine if you actually form a precipitate or if there's no reaction. So remember that no precipitate, you don't form anything that's a solid, then that means there's no reaction. Neutralization reactions must have water as a product. So this is kind of a review, and it's ways to kind of narrow down what it is that you're looking at. We'll start next week's class with identifying reactions. I didn't want to do a bunch of that now, just because it'll take a little bit for it to kind of marinate in your brain. So as you're doing your homework over the weekend, because you do have Chapter 7 homework, even though we have an exam, hopefully it'll kind of permeate your brain and we'll be able to do some more review next week. But this is the cheat sheet. Let me know when you've got it jotted down so we can move on to balancing equations. Oh, and then I gotta wait. My bad. Okay. Balancing chemical equations. This is the last part of Chapter 7. The goal for balancing equations is to have the same number of atoms of each element on both sides of the equation. So that's our goal. To do that, you first have to take stock of what you have. So we've got a simple chemical equation here. We've got hydrogen gas and nitrogen gas coming together to make ammonia. We've only got two elements here, hydrogen and nitrogen. I put an R for my reactant side, a P for my product side, and I count how many of each element I see. The subscripts here mean that I have two hydrogen atoms. Same thing for the nitrogen. I've got two. On the product side, how many hydrogens do I have? I've got 3. How many nitrogen atoms do I have? We've only got 1. So clearly we're not balanced here. We can't just make hydrogen appear out of nowhere, and we can't make the nitrogen disappear. In order to balance this, we're going to add coefficients. A coefficient is just a number in front of the compound that multiplies how many of each compound we have, and it'll balance out the number of atoms. We have to use the lowest common denominators so that we can multiply and get the same number of atoms on each side. So the lowest common denominator between 2 and 3 is going to be 6. That's the smallest number that you can use and say, okay, 6 divided by 2 is 3, 6 divided by 3 is 2. Smallest number that you can do that with. To get there, we're going to put a 3 in front of where we see the hydrogen. And we're going to put a 2 in front of where we see the hydrogen on the product side. Notice that I did not change the subscripts. So the little numbers, leave them alone. No touch. No touch. No touchy. Don't do anything to them. We add a number in front. Then I make a new chart. If you have taken chemistry before and you feel comfortable doing it without writing the charts, go for the gold. If sometimes you miss little details here and there, you should make the chart. Make a chart, figure out what you're changing, make the change, and then count how many atoms you have after doing those changes. Then you'll see what's balanced and what's not. I do this for 2 reasons. 1, you keep track of what you did, so that if you get to the end and you're like, wait, that's not balanced, you can catch any math errors more easily. But 2, there are multiple times where you can catch mistakes. So I definitely recommend making these charts and recording kind of what changes you're making along the way, because this is just guess and check. There's no formula for figuring out how to balance an equation. So now that we've changed our hydrogens, we now have 3 times 2, which is 6 hydrogens, on the reactant side. On the product side, we have 2 ammonias, and each of them have 3 hydrogens, which means we've got 6. On the reactant side for nitrogen, we haven't done anything, so that's still 2. On the product side, however, since we put that 2 in front of the ammonia, we now have 2 times 1, which also gives us 2. So we've got the same number of atoms of each element on both sides, and that means this equation is balanced. If I were to ask a question like, what are the coefficients in the balanced equation from reactants to products, then my coefficients would be 3, 1, and 2. When you don't have a coefficient in front, there's no number, it's just a 1. We don't write in the 1, we just kind of imply there's only 1 here. How does that feel? Simple equation to balance. Okay. Let's do another. This time, we've got a chemical equation that we have to write out from the written description. Manganese metal, that's that. Aqueous nickel 2 nitrate. And it produces manganese 2 nitrate and nickel metal. Before we start balancing anything, what kind of reaction is this? It's not a double replacement, it's a single replacement. Double replacement, we would have 2 aqueous solutions. Here, we're adding a metal into an aqueous solution. So that's a single replacement. So we've got our equation, but it's not, but we have to check and see if it's balanced. So I make my chart. Notice how we have the nitrate. I see nitrate on both sides of my equation. Because I see it on both sides, I can keep it together as a unit and balance it that way. I don't have to balance the individual nitrogens and the individual oxygens. I can simply we wrote out our chemical equation from the written description. Now we need to check and see, do we have to balance this? We count up how many atoms of each element on each side, and we keep the nitrate ion as one group. Reactant side, I've got 1 manganese, 1 nickel, and 2 nitrate ions. I look at the reactant side, or the product side, excuse me. I've got 1 manganese, 2 nitrates, and 1 nickel. So this one is already balanced. And my coefficients are 1, 1, 1, and 1. So when you're doing these, you may come across some reactions or equations that are already balanced. If you do, then your work is done. Let me know if you're still with me. So we don't have 2 for the manganese because, so if you're talking about on the product side, this 2 is only for the nitrate. Same thing with the nickel nitrate, the nickel 2 nitrate. Only the numbers out in front multiply everything. So if I had a number out here, then I'd have more than 1 manganese. Here's another one. I want you to try it. Iron is heated with fluorine gas to yield solid iron 3 fluoride. I'll give you 2 minutes to write out your equation and start balancing, and then I'll jump in and get started. Here we go. This is more practice in writing out that chemical equation from the written description. We've got iron and fluorine gas. Fluorine gas is one of those diatomic molecules. So it is F2. That's how you find it in nature. And those things come together to make iron 3 fluoride. That's the equation we're starting with just from reading the description. Now we have to make our table and check to see if it's balanced already or if we need to do some changing around with coefficients. There's only 2 elements here. We've got iron and we've got fluorine. Reactant side, we've got 1 iron and 2 fluorines because of that subscript. Product side, we've got 1 iron and 3 fluorines. So we need to do a little bit of work. Getting this answer right is predicated on being able to take something like iron 3 fluoride and write the chemical formula. So again, chapter 6 is key. We're going to find our lowest common denominator between 2 and 3, which is 6. That means I need to put a 3 in front of the compound with the fluorine, which is just fluorine gas. And I need to put a 2 in front of the compound that has fluorine on the product side. Then I do another table to see where I'm at. Reactant side, I didn't touch the iron, so I've still got 1. With the fluorine, I've got 3 molecules of fluorine gas, and each one of them has 2 fluorine atoms, for a total of 6 atoms. On the product side, I placed a 2 in front of the iron 3 chloride. So now I've got 2 iron 3 chlorides and each of them has one iron atom for a total of 2 iron atoms. I've also got 6 fluorine atoms. My fluorines, they're balanced. Iron, now it's not balanced. The lowest common denominator between 1 and 2 is going to be 2. That means we're placing a 2 in front of the iron on the reactant side. We do one more table, and this should show that everything is balanced. If it's not, then you have to figure out where you went wrong. Reactant side, I've got 2 irons, and 3 times 2 equals 6 fluorine atoms, which we haven't changed that since the last time. And then we've got 2 times 1 to give us 2 irons, and 2 times 3 to give us 6 fluorines. Now we're balanced. Our coefficients are 2, 3, and 2. Questions on this? Good, good. Then that's it. We've got reminders. Chapter 7 Mastering Chemistry assignments are due on Sunday. I know you have an exam this week too. I just can't fit it all in. Chapter 7 shouldn't be that bad. So make sure you get that homework done. There's no chapter check-in, just the Mastering Chemistry. You've got exam 3 this week. It'll be available tomorrow morning by 9, and it will be gone Friday, March 19th at 11:59 p.m. So make sure that you start the exam somewhere in that window. I've got office hours today from 11:30 to 1. If you have questions, come on through. If you need to make an appointment with me because my office hours don't work, you can either hit me up now, right after class, or just send me a course message. Outside of that, we're done. So if you have no questions, you're free to go.